Hi everyone, my name is Luis Bello, and I'm going to talk about codes decoding a constant fraction of errors. This is joint work with Jan Hasla and Alex Samoranitsky. So for the purpose of this talk, it is best to view error correcting codes as the solution to the following challenge. Suppose you have a k-bit message and you want to send it through a noisy medium to a second party. The second party wants to decode it, but instead of getting the original message that you sent, he gets a noisy version of it. So what do? Instead of sending the original message, you send an encoding of it. And this encoding is known as an error correcting code. We shall focus on a specific type of such encodings, linear maps. Okay, so definition, a binary linear error correcting code is a linear subspace of F2 to the n. And note that we disregard the mapping and only keep the image. We only refer to the image of this mapping. So perhaps the most basic property of an error correcting code is its rate, which is defined by the dimension of V divided by N. So this captures the amount of information each bit in the vector carries. So for instance, if the rate is 1/3, then this means that each vector that you send carries n over 3 bits of information. And therefore we want to maximize this as much as possible. So let's try to understand how we model noise. So the first model was proposed by Hamming, in which corruptions are adversarial. So we can imagine an adversary choosing the worst possible locations to corrupt, though he needs to choose a bounded number of them. So there are two prominent types of corruption. The first one being erasures, in which the adversary replaces bits with a question mark, as you can see here. And the second one being errors or flips, in which the adversary flips bits. Okay. The behavior in this setting is completely determined by something called the minimum distance of the code, which is defined as the Hamming distance between the two closest vectors, distinct vectors in your code. So we will not be discussing Hamming's model, though it will be a good reference. We're going to focus on Shannons model, in which corruptions are random, and we want to recover the original code word with high probability. So for erasures, we have the binary erasure channel with erasure probability P. This is defined by replacing every bit with a question mark independently for every bit. So this is one way to model random erasures. And for errors or flips, we have the binary symmetric channel in which every bit is flipped independently with probability P. We can also consider a continuous setting in which we add a Gaussian independently, a Gaussian of some variance independently to every bit. So this is sort of a continuous setting called the Gaussian noise channel. And if you're not familiar with Shannon's model, then these are basically the only examples you should keep in mind. But these examples are part of a larger family of something called binary memoryless symmetric channels, or BMS channels. So what is a channel? A channel is basically, you can think about it as a box. A channel W is a box W that gets a binary input, and it outputs a symbol. This symbol can be binary, but it can also be non-binary, like a question mark, as in the erasure channel. So memoryless means that you do that for any coordinate independently. And symmetric basically means that the fashion in which you corrupt 0 and 1 is symmetric. So for instance, if you flip 0 and 1 with different probabilities, then this is not a symmetric channel. So this is how we model random noise. But what about the decoding? So for the decoding, we consider the so-called map decoder, which is a shorthand for maximum a posteriori decoder. And for those that are not familiar with it, you can just think about the optimal decoder. So the map decoder takes the noisy message Y and looks for the vector V in the subspace that maximizes this probability, that the probability that this vector was sent given that you received Y. So again, if you're not familiar with it, just think about the optimal decoder like this. The decoder just chooses the best fit. And how do you define the error with respect to this channel? You define it simply as the probability that this so-called map decoder or the optimal decoder fails. So x here is the random vector from V, and y is just the result of transmitting x through that noisy channel W. Okay, so this is how we define the error. And we say that the family of codes decode over channel W if asymptotically this error goes to 0. Okay, so we're now basically in a position to state our result, but before that, I want to define two quantities for BMS channel. So the first one being the capacity of a channel W, which is the largest achievable rate for this channel. This means that you consider all possible encodings, all possible error correcting codes that decode successfully over this channel, and you take the maximum rate among all these codes. So for instance, the capacity of the binary erasure channel with erasure probability lambda is 1 minus lambda. This means that if you take a code with rate larger than this, then you cannot hope that it decodes successfully over this channel. And there are also codes, even random codes, that achieve this max. So this is capacity. You can also define it for other channel, for every BMS channel. And there's also something called the bataclan parameter, this ZW, which is just the parameter between 0 and 1. I'm not going to explain the meaning of it. But for instance, the bataclan parameter of the binary erasure channel with parameter lambda is lambda. The bataclan parameter of the binary symmetric channel with flip probability P is the square root of 4 times P times 1 minus P, etc. So this is just a parameter, and note that as the channel gets noisier, this parameter gets closer to 1. Okay, so let me just give you a taste of what is known in this general setting. This is just the tip of the iceberg. So random linear codes achieve capacity for any BMS channel. Basically, random codes are optimal. We do know how to construct explicit error correcting codes for that achieve capacity for any given BMS channel. And actually with efficient encoding and decoding, these are called polar codes. They were constructed by Erican in 2009. And we do know that if your code is satisfied some symmetry property called double transitivity, then this code achieves capacity for the BSC with an asterisk. But we're going to talk about this third result later on, so let me just wait on that. So what is our first result? So let me give you a qualitative statement. We prove that any binary linear code that can decode over the binary erasure channel can decode over any BMS channel with a small enough bataclan parameter. So for instance, if you can decode some constant fraction of random erasures, you can actually decode from some other constant fraction of random errors. You can decode from additive Gaussian noise for some constant variance, etc. And this actually goes the other way around, but let me not get into this. So quantitatively, this looks like this. So you take a binary linear code V, and you assume that the error probability is smaller than this. This is really minute in the asymptotic setting. Then for any BMSW, the error probability for this channel with respect to V is at most this. And note that if this ZW, this bataclan parameter, is strictly smaller than 2 lambda minus 1, I remind you that lambda is the erasure probability, then you can see that this is small and you can decode over this channel. So for instance, for the binary symmetric channel, I will prove that any family of binary linear codes that can decode over the binary erasure channel with erasure probability lambda can decode from this many fraction of random flips of random errors and can decode over the additive Gaussian noise for this variance, with this variance. Okay. So even if you start with a family of codes that are capacity achieving for the binary erasure channel, this result does not give you probably achieving capacity for, say, the binary symmetric channel or for any other BMS channel for that matter. Okay, so this concludes our first result. So what about our second result? It concerns doubly transitive codes. So let me define double transitivity. So for any binary linear code V, its permutation group or its symmetry group is defined by all the permutations over the coordinates of the vectors in V, for which the subspace V is invariant under. So for instance, if for any vector in V, if you permute say the first and third coordinate, this gives you another vector which is still in V, then this transposition belongs to this symmetry group, this permutation group. And we shall say that V is doubly transitive if this group is doubly transitive, namely that for any distinct indices, two indices that you want to map them to like any two distinct indices, there is a permutation in the group that does that. So this is double transitivity. And in 2016, Kudaker, Kumar, Mandeli, Fitzer, Sassublum, and Urbanke proved that any family of binary linear codes, which is doubly transitive and constant rate R, is capacity achieving for the binary erasure channel. But there is a catch here. This is true with respect to something called bitmap decoding. So what is bitmap decoding? You can think about it as the same optimal decoder trying to find the best fit, but now instead of asking whether this optimal decoder found the original code word yes or no, you ask, well, on how many bits this optimal decoder is correct. And if an expectation, the optimal decoder, that the so-called map decoder is correct over, say, 1 minus something that tends to 0 fraction of the coordinates in expectation, that then you say that the code, the family can decode over the binary erasure channel. And again, capacity achieving means that this code actually gives you, this family gives you the optimal trade-off between the rate and the fraction of random erasures, which I remind you that is the rate equals 1 minus the erasure probability. So this is what they proved. This is the first bullet. And in the case that the distance is sufficiently large, say larger than n over polylog n, so this is definitely plausible and it holds for many cases, then the family actually achieved capacity for the binary erasure channel for this standard block map decoding, standard map decoding without this annoying bitmap decoding. And they also proved that a specific family of codes called the Reed-Muller code is capacity of constant rate is capacity achieving for the binary erasure channel under the standard map decoding, block map decoding. So first, what is the Reed-Muller code? It is the code defined as the truth table or evaluation vectors of multivariate multilinear polynomials of bounded degree. So for instance, the Reed-Muller code of rate 1/2 is simply the evaluation vectors or the truth table of all polynomials with n variables, multilinear polynomials with n variables and degree at most m over 2. So this is the Reed-Muller code. It is really an old family of codes. It is well studied, many applications in TCS. And the reason this third bullet is here, because this family is doubly transitive, is because its minimum distance is square root of n. So if you want to get block map decoding, you need to argue something more than just using the first bullet. You cannot use the first bullet. So as a direct application, if you apply the first result, you can conclude that this family, these Reed-Muller codes of constant rate R, can actually decode over any BMS channel with its bataclan parameter being smaller than this. In particular, it can decode this many constant fraction of random errors and this additive Gaussian noise with this variance. And for instance, it was not known whether even a Reed-Muller code with a tiny constant rate can decode, say, tiny constant fraction of random errors, for instance. So there were some results in the like in the vanishing rate regime, but I don't want to get into this. And this basically the same holds not only for the real Muller codes, but also for codes with, say, distance of mod n over polynomial. So this is not yet our first result. So note that what can you say about codes with distance, say, n to the 0.2, which are doubly transitive? Because this minute technicality is not actually that minute in our setting. So our second result tackles that. We prove that any family of doubly transitive binary linear codes of given constant rate R and distance, say at most n to the alpha, where alpha is some constant, this family can decode over a given BMS channel with bataclan parameters smaller than something. And this something depends on R, on the rate, and on the distance. Okay. For instance, if you take a family of doubly transitive codes with rate 0.8 and minimum distance square root of n, then this tells you that this family can decode from 0.024 fraction of random errors, random flips. So here's a figure of this result. So this corresponds to the binary symmetric channel. So here, the vertical axis is the parameter of P, the probability of the bits being flipped. The horizontal axis is the rate. And each curve corresponds to, a solid curve corresponds to some distance bound. So for instance, the yellow curve corresponds to the distance being, say, n over polylog n, the purple, the distance being n to the 0.9, etc., etc., etc. And this is the trade-off that this result gives you. And you can see that this trade-off deteriorates as the distance gets smaller. And in the dashed line, you can see the optimal trade-off, the capacity. Okay. So this concludes our second result. So let me talk just a bit about the proofs. So the proofs basically use an inequality on Boolean functions proved by Samournitsky. So to state this inequality, I will need two definitions. So we define the noise operator. So for any Boolean function f, and by Boolean function, I mean a function from the Boolean hypercube to the reals, and this parameter rho, we define this T rho of f, which is basically a function. It's an averaging operator. You can see that it sort of takes the average of points close to x in some sense. And we defined another operator called conditional expectation that for every function and subset of the coordinate, it is another averaging operator. You can see that it sort of takes the average over the coordinates in S. So these are two operators. And Samournitsky proved in 2019 and later improved it in 2020 that for any non-negative Boolean function, you have this inequality. You can see that on the left-hand side, you have the L2 norm of the noise operator, and on the right-hand side, you sort of have the expected L2 norm of the conditional expectation operator. So this is just an inequality. So let me just make two remarks. The first one being that Samournitsky actually proved a more general inequality for the LQ norm, but we do not need the general version. And the version for the L2 norm surprisingly has an elementary short proof. And this means that our first result basically has a 2-3 pages long self-contained proof, which is nice. The second remark I want to make is that I want to emphasize that at least the first result directly follows from this inequality. So all the technical fireworks, so-called heavy lifting is in this inequality. And not only that, in hindsight, the first result follows from this inequality plus from this paper and plus some well-known manipulations. So let's get on with the proof. So basically you apply this inequality for the function f, which is the characteristic function of the subspace V. In order to state what you get, we will need the following definitions. So the weight distribution. So for every vector V, we define its weight as simply the number of ones in that vector, and the weight distribution of a subspace V is defined as the sequence enumerating how many vectors you have in V with weight exactly I. So AI is simply the number of vectors in V with weight exactly I. We find for a subset of the coordinates S and a subspace V, we define V sub S as the restriction of V to the coordinates of S, this is a subspace, a linear subspace, and the dual space as the set of all vectors U, such that the inner product with any vector V and V is 0. So this is the dual space. So if we plug to Samoylnitsky's inequality the characteristic function of a linear code V, then this is what you get, where AI is the weight distribution and V sub S is the restricted subspace of the dual code. Okay, so you can actually simplify the right-hand side to get a slightly more meaningful expression, arguably more meaningful, which is the entropy of X given Y, where X is a random vector in V, and Y is the result of transmitting this vector through the binary erasure channel with erasure probability lambda. Okay, and let me just continue just a bit. And the last missing piece is something called the bataclan bound, which is the following. If you take a linear code V, AI being its weight distribution, and a BMS channel W, then the error probability of transmitting a vector through this channel W is bounded by this sum of AI times the bataclan parameter to the power of I. So if you can imagine that this 2 to the power of lambda minus y minus 1 equals this bataclan parameter, so you just need to show that the right-hand side is small. So for the first result, this will be small sort of by assumption, because if you assume that your code is capacity achieving or not capacity achieving, can decode lambda fraction of random erasures, then this entropy will basically be small. So this is it. So what about the second result? So you can see here that I wrote that the derivative of this entropy equals actually n times this lowercase h of lambda, and this h of lambda, lowercase h of lambda, is called the exit function. And in the case of doubly transitive codes, it is actually more convenient, or there is an approach to prove that actually this is small. So this is why this is appearing here. So this is the exit function. So what about doubly transitive codes? So as I said, in their paper, Kudeker, Kumar, Mandeli, Fitzer, Sasoglu, and Urbanke outlined an approach for proving that this exit function is small, or gave a bound in this exit function. So this is not enough if you consider codes with, say, small distance, but if you incorporate it with another bound, which is this one, and you sort of optimize, then you do get the second result. And actually these two bounds comes from tools from Boolean analysis. And that's it, basically. So thank you very much.